Hi. So how many dimensions does a vector have? It's a kind of a trick question. And I'm not going to give you the official answer. I'm just going to confuse you. Well, actually, here's the official answer. If you ask a mathematician, he will tell you, well, the number of dimension is the number of scalars. Yeah? So, however, you know, I'm a programmer, and I can see a vector as a collection, and to me, I mean, if you're an APLer, you would think a vector has one dimension, right? Because it goes into one direction. However, if you do charting, you realize that to plot a vector, you need 2 degrees of freedom. You need an xy plane, an x for index, and a y for values. And if you're a geek, you will ask, oh, is it real or is it complex? And we'll duck that, right? So let's stick to real, you know, real simple. So what we're interested in is degrees of freedom of a real vector as representing something, you know, something real, a sampling of something with 1 degree of freedom. So if we generate a vector like that, we can say that its domain has 1 degree of freedom, so I can choose an x value over a one-dimensional line, and the image of the function has 1 degree of freedom too. Yeah? And for example, the domain could be time, like in a time series, and the image could be acoustic pressure. So here, this could be a sound wave, yeah? A weird one, but a sound wave. However, when we think about the sound, it really has 2 degrees of freedom. I mean, you can have any kind of, you may have sound at any point in time and frequency, right? For example, a chord is a superposition of different frequency at a given time, and a melody is a sequence of different frequency at different times. So if we really want to view a vector just as our ear do, we need more than that. And namely, we need a notion of frequency. So if we plot the sound, we can easily, oh, let me try if we can hear the sound. So I'm not sure it will work. Oh. So here's the sound, and we can easily see the loudness of the sound. So the peaks there are like the percussive hits of the instruments, and then you can see the resonance fading away. However, it's hard to tell which frequency are present at which point. There are cases where it seems easy, and there are cases where it's clearly difficult. But some people have solved the problem for us, and they come up with this Fourier transform thing. So to start with, what's a vector? The way you would see it in that context is that you turn a list of scalars into a vector by having a list of base vectors, which here are impulses, so that means it's 1 in 1 point and 0 all over the place. We call that an impulse. And you have 1 impulse per possible position, right? So I'm showing only the first few ones. And you would weight each of these vectors by the scalar at each position, and then you sum them up. So it's a plus dot times, basically. And the Fourier transform, or the Fourier theory, tells us that you can represent a vector like that, but you can also represent it as a sum of signs. And signs have well-defined frequency. So the first sign, the 0th sign does 0 cycle over the vector. Sign number 1 does 1 cycle, sign number 2 does 2 cycles, and so on. And then you would have weights for each of those. I will call them atoms, because I like the word. It's like the atoms we're manipulating to build up things. And then again, so you would scale them with a scalar, and then sum it up and get a signal. So if you have a frequency representation of a sound, if you have scalars that are frequency-wise, one scalar per frequency, you just weight them and sum them up. And what you would get would be the time representation. So you can move on from back and forth from frequency representation into time representation back and forth with a Fourier transform. Two things I would like to mention here. The first one is, if you look at the signs, so we have endpoints there, and so we're going 1 cycle, 2 cycle, 3 cycle, blah, 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 and when we reach n cycles on a vector that has endpoints, well, that means you do 1 cycle between each sample. So basically, each sample will have the same value. So what happens is, as you go down, you come back to the top, right? So the nth atom is actually the 0th one. That means that when you're thinking in Fourier analysis, frequency wrap. And for similar reasons, time wraps too. So you can think that the second atom on the time there, the second atom there is like the successor of the first one, yeah? And this one is the successor of this one. And again, when you reach the last one, there's only one successor, one possible successor, which is the first one there. So the point here is that as soon as you do Fourier analysis on discrete vectors, it all wraps in all directions, in frequency and in time. Second remark is that, so just bear in mind that you are looking at matrices here. So this list of vectors are matrices. And the matrix on the left is the identity matrix. I don't know if you've noticed. Yeah? So it's a diagonal of ones. So it would turn a time vector into a time vector. And the second one on the right is the Fourier transform matrix. So it would turn, well, I'm skipping some minor details, but basically it would turn a time representation into a frequency representation back and forth with perfect reconstruction, which that means that both representations have the same information. So here's our matrix. And here's how we compute it. So if you're an APLer, these two lines just say the same thing, right? However, if you're a mathematician, the first one is called a scalar product, and the second one is called a matrix multiplication. So I think that's neat. I mean, APL got it right once more. That was just an aside. The thing I would like you to remember, first of all, the Fourier transform is non-local. So because these signs are non-zero, if you change a single scalar in the input, it will affect every single scalar in the output. The second thing is that the concept of frequency requires complex scalars, because you cannot just scale the magnitude of those signs, you also have to scale the phase, right? Like the time-wise displacement. And complex numbers, by accident, happen to be perfectly suitable to scale signs. And the last thing, as I said, is that those atom matrix wrap both in time and frequency. So how does it look like? On the top here, you have the time-wise representation of the sound we heard earlier. So those sharp peaks are like percussive events, very well localized in time. And at the bottom there, you have the spectrum, so the frequency representation of the same thing, right? It has the same information. And those peaks there give you which harmonics, which parts of the sound are close to pure science, the notes you were hearing in the sound. So we kind of have two ways to project the sound, except that the top one is real, and the second one is complex. I'm only showing you the magnitude there, but if I zoom on one of those frequency peaks, right, if I zoom on one of those, and I really want to represent it, I need to show you the magnitude with a peak there, and I also need you to show the phase. And actually the phase there, it looks noisy, but if you look carefully and spend a lot of time looking at it, you realize that it actually bears the time localization information. So to start with, we looked at a sound as something that has one degree of freedom domain and 1 degree of freedom image. But as we introduced the concept of frequency, we got this. So we have a 1D domain, which is frequency, and we have a 2D image. Oh, and by the way, for those who know about the Fourier transform, you might think, oh yeah, but because it's a real signal, it's redundant, right? It's symmetrical. So you could say that we have doubled the number of dimensions by artificially halving the numbers of samples. However, that doesn't really hold, because the formula is right there, and you need one more. I won't explain why, but if your vector has 6 real numbers, you will need 4 complex numbers, not 3. So it's not as simple as it looks. And that's not what we wanted, right? What we wanted was to have a 2D domain, right? And we end up with a 2D image, so we're not there yet. We need a notion of time-limited frequency, and talking about time limitation, okay. So now we're going to push it a little further. We want to have atoms that have well-defined frequency, but that are also localized in time, right? So instead of having a list of atoms, we are going to have a matrix of atoms. And so the vertical axis here will be frequency. You can see that the atoms have higher frequency, the higher atom has higher frequency. And on the x-axis, we would have times, right? So the right atom are localized on the right hand of the vector. And obviously, you would have many more of these. I'm only showing 6, just for illustration. And once we do that, we get something very cool. It was actually what we were looking for. It's called a spectrogram. And it's really like a time-frequency plane. So you have time on the x-axis, frequency on the y-axis, and you can actually see the sound events just as the ear perceives them. So the vertical bars are percussive events, so time-localized events, dunk, 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 and the horizontal lines are like harmonics, like things that sounds like pure science. And if you squish it along one of the dimensions, you get either the time representation above or the frequency representation on the right. However, remember that the domain is complex, right? I'm only showing the magnitude here with false colors. But to be true, to be fair, I would need to represent the phase information too. So what I'm going to do is to represent magnitude as a z height, right, pointing towards you, and then represent the phase with a coloring. And the color is very suitable for phase because it cycles. You can have blue, green, yellow, red, blue, or purple, blue. It cycles, so it's reasonably. So this is what it really looks like. Right? Can you see that it's sort of a 3D thing with psychedelic colorings? Yeah, that's more accurate. Actually, we're not there yet, because remember I told you that things wrap in time and frequency. So to be fair, I need to be more precise, and I need to wrap it around in both dimensions and get something like that. So that's what a sound looks like according to Fourier analysis. So we wanted a 1D image over a 2D domain, and we get a 2D image over a 2D domain. So is this a happy hand? Guess what? No. I don't like the term uncertainty, which I think comes from quantum physics, where it has its own meaning. I prefer to talk about dispersion, because here in this case we have full information about the vector, right? There is nothing uncertain. So a mathematician from the audience tried to dissuade me from doing that, but I can't help it. That's the way I understand it. And what this says is that you can't avoid a dispersion either in time or frequency. There's nothing you can do about it. You just have to make a choice. So if you try to squish a signal or an atom in time, it will suddenly spread in frequency, and you can't help it, and conversely. So in the case of a continuous Fourier transform, the measure of dispersion is the standard deviation, but we're doing vectors, so we're doing discrete Fourier transform, in which case the dispersion is the number of non-zero values. So if you try to have a well-localized thing with zeros on the edges, it will spread in the other domain. That means that a signal cannot be at the same time, at the same something time-limited and frequency-limited. You have to make a choice. That means that information is non-local in at least one of those two domains. You can't localize things in both domains. And there's also this weird thing that then time-frequency information depends on the choice of frame. I mean, the choice of the atoms we saw there, because you made a choice, right? You take a sign and you windowed it, and you made a choice there. And so somehow the time-frequency information is subjective, which is very disturbing. So here's an illustration of it. So still the same signal, but with two different kind of frames. One which is well localized in time, and one which is well localized in frequency. And you have to make a choice. You can't have the best of both worlds. They are different representations. So to start with, we could think of a vector as, 1 degree of freedom over 1 degree of freedom. It's all nice, fair, and square. Nice and easy, but as soon as we try to understand the concept of frequency, then a vector is a donut with mountains and valleys and some psychedelic coloring, and actually the shape of it and the color of it depends on the model of camera you're using to take a picture of it. So I hope you are as confused as me, because that was my goal. So basically, if you want to introduce the second domain, if you want these two domains to coexist, the dual domain is both introduced and restricted by the choice of frame. And by the way, there are more possible frames than signals, right? There are more models of cameras than there are models of donuts, which again is very weird. So that's it for me. I hope you're confused. You can try asking questions. I will try answering something else that I don't know. And if you don't have questions, I have one. So here's my question. It has to do with complex numbers, because there was this thing that if you take the time representation of a real vector and you take the Fourier transform, you get something that is complex. So it's like you turn, just by taking this invertible Fourier transform, you transform something that is real into something that is complex. And where is that second dimension coming from? It doesn't make sense, right? And it makes me think that for the ancient Greeks, I mean, there was nothing but natural numbers, right? Integers. And so a number would be a ratio of two integers. And if you ask Pythagoras, how do you add two numbers? He would tell you, oh, here's the equation that gives you. And you have this very complex formula that tells you how to add two rationals. And we've all struggled with that in high school, right? It's a very complex way of looking at it. And obviously, if you ask a modern Greek, how do you add two numbers? He would go, what do you mean, add two numbers? You just add them, right? There's no formula. A plus B is A plus B. What do you mean? And maybe we're in the same kind of situation, right? Because at the moment, if you say, how do you multiply two complex numbers in Cartesian representation? You have to use this very complex formula because the unit of thinking we have is a real number. And it forces us to look at complex numbers as a 2D entity. But is it really so? Is it really fundamentally a 2D entity? I'm not sure about that. And I would like to hope that we're the ancient Greeks. Yeah? Why should scalars be 2D? It doesn't make sense. Can the brain cope with complex numbers not being 2D? That's my question. I don't have a good answer to anything. I think we're done. Well, thank you for listening.
Thank you, Nick.